Hello everyone, is the Prophet Michael David, aka Aries, and today we are going to go over my second video about perfect numbers, Mersenne primes, and the Collatz game, and how they're all related. Alright, that is the thumbnail of this video, and that's my, call it a conjecture, call it proof. I hate to sound like Pierre de Fermat, but it's right. But I will read it to you and explain it to you right now. Okay, all perfect numbers must fall on modulus lines in the form of A mod B, where A is the final digital root that square primes can be, and B is a final digital root that primes cannot be, and 3, A plus B equals 10. And of course, I mean excluding the first perfect number 6. That's the weirdo. That doesn't count. And the second part of the proof is, therefore, all perfect numbers must fall on modulus lines 1 mod 9, 4 mod 6, and 7 mod 3. So before I tell you why this is true, I wanted to give you the story of my inspiration and how I learned all this stuff. It was a couple years ago, and I saw that YouTube video online by a mathologer who I'd watched a few videos of, and I'd seen that Tesla stuff all over the internet, the whole 369, from spirituality stuff to religious stuff to other stuff. And so I really kind of wanted to know what the mathematics were behind it. And I watched the video and I instantly thought, I wonder what the digital root of the primes are, because I work with primes all the time. And I found out, I'm like, that's so weird. The digital root of the primes can be anything but 3, 6, or 9. They're anything but the ones that are connected with the lines. I was like, that's so weird. I could see it's got to be something in electricity too, or that's how Tesla saw it, something in the electricity. But so then the second thing I thought was, I wonder what the digital roots of the squares of primes look like, because I work with those all the time as well. And I found out that the only digital roots that squares of primes can be are 1, 4, and 7. And I was like, that's so weird. It's like the digital roots that the primes can't be on that graph got clicked by 1, and somehow that made them into digital roots that the prime squares have to be. I was like, that's so weird. That's so weird. Okay, most of you probably know what digital roots are by now, especially if you watched my last video, but I'll explain it one more time and I'll bring some religious stuff into it, just for funsies, I guess. So take the number 444. That is the Archangel Michael's number, that my namesake. And people have it tattoos of it all the time. 4 plus 4 plus 4 equals 12. So 12 is the first digital root of 444. 12 is a combination of 1 and 2, also holy, the alpha and the bet. And 1 plus 2 equals 3, Gimel. So that's why in a lot of numbers are holy that are associated with 12. But in a religious nutshell, that's what a digital root is. You can take any number as big as it is, add up all the digits in it, or all the numbers in it, and you get a new number. And that's the first digital root. And then you do that again, second digital root, if the number is big enough, until you get down to one singular number, and that is the final digital root of whatever number that you started digital routine in the first place. And everybody who is in the prime number game long enough, or that knows about digital roots as well, knows that base 9 is synonymous with digital roots. If you put numbers in base 9, it just kicks out all of the different digital roots. All the same numbers will always have the same digital root. And so that's exactly what I did. Okay, I'm gonna try not to confuse you. So as I've said before, you can use base 10 numbers because we understand those symbols, but when you graph them that way or in a spreadsheet, you can put them in whatever modulus that you want to. In this case, we did 9, so that's why it has 9 rows. And you can see all the numbers in each row. If you keep adding them up, they always digital root down to whatever row that is. And also, please don't be confused, I used my standard coloring. So the blue numbers are primes that are located on the 5 mod 6 line, and the green ones are numbers that are located on the 7 mod 6 line, because normally I graph stuff in mod 6, but I kept the color conventions the same. And the pink numbers are squares of primes. And as you can see, all of the primes, green or blue, have to be located on all of the lines except 3, 6, or 9, because we're in base 9. We're doing digital roots. And all of the squares of the primes, the pink ones, are only located on 1, 4, and 7. All right, that's a screenshot from the perfect numbers Wikipedia page and how it describes how perfect numbers relate to digital roots, or what people already know about it. So in other words, people already know, at least for the 51 known perfect numbers and everything, that they all fall on the 1 mod 9 line. So that part of my proof is nothing new. Okay, so now we're going to segue from digital roots to what exactly perfect numbers are in a geometrical sense, because thinking them in geometry is a great way to see what they actually are and why certain numbers can't be them. That's also straight from Wiki. And what this is saying is that all of the reciprocals of the factors of the perfect numbers have to add up to a geometric progression that equals 2. And why did I throw this in? Because we were talking about this just last video with the Collatz game. You see, it's just like the probabilities that we talked about in the last video, but instead of summing into a square like that, it's a 2. So it's 2 squares side by side. It's a rectangle, but the same principle applies. All right, so that's a screenshot of the factorization of the perfect number 8128. And if you look long enough at it, you can see that it's just 127, which is a Mersenne prime, times a bunch of 2's. That's all it is. It's one prime number times a bunch of 2's that happen to form a very large square. But like I said, the longer you look at it, that's what the perfect numbers are. But you can see how they have to balance out in the 2 columns. It needs enough 2's to get up that number, and just enough 2's to match it on the other side, so that all the factors multiply out to the same thing. But in the end, it's just one prime number, a Mersenne prime, times a bunch of 2's. All right, so now you're starting to see the type of symmetry that these perfect numbers manifest on like a 2-dimensional geometric series scale, and also the type of symmetry they have within just the number of 2's that they have in the numbers themselves. But how does the symmetry manifest itself at 3 dimensions? Well, here's how. Okay, firstly, apologies to Derek from Veritasium for the screenshot of the OG meme face, but it was a really clear screenshot of the best part of the video, and I do not regret it. Why it's the best part of the video is because that's how you should really think of what perfect numbers are. They're not magnitudes, they're not lines, they're not areas, they're volumes. And the best way to think about them is a stack of cubes that go, the bigger the prime number, the bigger the stack of cubes, and they make a large pyramid. But actually, if you look at it from far enough away and the perfect numbers are big enough, it's going to look like what's called a Shiva lingam. We've talked about this before. It's Indian, but that's exactly what it is. It would look like a squarish Shiva lingam. But that's what a perfect number is, just a stack of odd cubes. They can't be even, they have to be odds. a Shiva lingam. Okay, so now we're segueing into odd perfect numbers because that is one of the 2,000-year-old questions. Are there any odd perfect numbers? No. But what Descartes was trying to say and misspoke a little bit, and what Leonard Euler corrected was if there were an odd perfect number, it would have to be a very large prime multiplied by an odd square. It can't be even, it has to be an odd square. So it could be a very large prime multiplied by 9, 3 squared, or multiplied by 25, 5 squared, or 7 squared, or 9 squared, or 11 squared. It doesn't have to be a prime square, it just has to be an odd square. But since all perfect numbers up till now are a large prime, which is odd, multiplied by some factor of 2, which happens to be a square, it's always even. Because an odd times an even is an even, but an odd times an odd is an odd. So in conclusion, if there were an odd perfect number, which there isn't, it would have to be a prime multiplied by an odd square. But for some reason, that structure, that three-dimensional structure, does not allow that. And that's what I'm working on now. But my proof that it still holds for reasons I will detail at the end of this video. All right, once again, that is my Collatz algorithm, and I'm throwing that in there because I always try to, but also because we're going to segue into Collatz, I'm finally going to tell you how perfect numbers and Mersenne primes are related to the Collatz game, as I promised to last video. All right, and lastly, before I start, that screenshot, you should screenshot yourself. It's straight from Wiki, but that's the first few Mersenne primes and their corresponding perfect numbers. So you can start doing math on them themselves. Because what I'm going to teach you right now is it's really easy to find what mod line anything is located on. So what that is for anything in the form of A mod B, all you have to do to find out if your number falls on that A mod B line is you take your number and subtract A and then divide by B. And then if it comes up a whole number, it's located on that line. So I'll give you 3 examples from my proof and everything. If you want to find out if any number in the universe falls on the 1 mod 9 line, all you have to do is take that number, minus 1, and then divide by 9. If it's a whole number, it does. That gives you the nth number that it is on the mod line. So second example, if you want to find out if any number is on the 4 mod 6 line, you subtract 4, divide by 6. And that'll give you, if it's a whole number, that'll give you the nth number on that mod line. One last one. If you want to find out if any number is on the 7 mod 3 line, you subtract 7, divide by 3. And if it's a whole number, that is the nth number on that mod line. Okay, at this point, that should be a mind-blowing screenshot. So all the golds are Mersenne primes, as you can see from my previous screenshot and everything. And if you watched my last video, you could see that I was trying to form 3x plus 1 divided by 2, 3x plus 1 divided by 2, chains that would go up to infinity, but they would always break. And as you can see, the longest chains, some of them, but whenever a Mersenne prime gold number comes up, it has a very long 3x plus 1 divided by 2, 3x plus 1 divided by 2 chain. And they always are the start of those chains when they come up. Man, I could talk about that single screenshot for hours. I've stared at it for hours. It's chock full of information. But what I also found was the 2 parts of the real or perfect numbers, the Mersenne and the square, I could find with algebraic expressions, except the difference was I didn't use just a series of 2's or primes. I just used the previous Mersenne prime. So in those equations, M1 just means the first Mersenne prime, and then M2 is the one after that. Except it doesn't catch them all. It just catch, let's call them possible Mersenne primes. But as you can see, you can generate them in other ways, just like Euclid thought or feared, using algebraic means. You don't have to use the exponential stuff. So now in conclusion, I'm going to explain while my proof and the information I showed you in this video solves both outstanding questions about perfect numbers, which are number one, are there any odd perfect numbers? And number two, are there an infinite amount of perfect numbers? And are there an infinite amount of Mersenne primes? All right, first we're going to do the are there an infinite amount of Mersenne primes in perfect numbers? Okay, from that screenshot, are there an infinite amount of Mersenne primes and therefore an infinite amount of perfect numbers? Yes. Why? Because in not all, but in some of the 3x chains that are formed in the Collatz game, when you're trying to get a number that goes up into infinity, it will always start with a Mersenne prime, and it'll always go up real fast. And while there are an infinite amount of chains, and not all of them, some of them will always start with a Mersenne prime. And so you need an infinite amount of Mersenne primes for the Collatz game up to infinity. In other words, if you wanted to break your computer real bad, all you have to do is pick a very large Mersenne prime and try to play the Collatz game with it. Because what it's going to do is it's going to 3x plus 1, only down by 2, 3x plus 1, only down by 2, like an absurd amount of times. And the number will just get so big that it'll break your computer. And finally, why are there no odd perfect numbers? Because they are required to lie on the 4 mod 6 line, as well as the 1 mod 9 line and the 7 mod 3 line. And the 1 mod 9 line and the 7 mod 3 line are not a problem because they alternate between odd and even. Any number on that line can be odd or even. There's a 50-50 chance. But to lie on the 4 mod 6 line, you must be even, because an even plus an even is an even. So now in a little conclusion discussion, you might be thinking, well, I mean, there's only 51 that's ever been discovered. How can you prove that they're all on the 4 mod 6 line? Well, you could say the same thing about the 1 mod 9 line. How can you prove that they all digital root to 1? Or you could say even numbers in general. How can you prove that all prime numbers have to end in 1, 3, 7, and 9 if we have no way to go to infinity? You know, you just have to be convinced that some patterns will hold. And in this case, with my proof, if you had an odd perfect number, you don't have to worry about the constraints of Euler or Descartes. What I'm saying is that it would have to be a number that falls on the 1 mod 9 line and the 7 mod 3 line, but it didn't fall on the 4 mod 6 line. And that would make it an odd number, but that would also break the symmetry because, as I started the video out with in the Tesla thing, the 369, like all numbers conform to all of them because those are all of the digital roots of the primes in or the ones that can't be in all of the digital roots that the square primes have to be. So there's a very much symmetry to it that would be totally broken if they only satisfy 2 out of the 3 constraints. All right, so that's for now the end of my proof on perfect numbers and why there have to be an infinite number and there can be no odd perfect numbers. Again, I can't dumb it down more than this. I'm not calling you guys dumb, just any mathematicians that see this and don't understand it. All right, I am going to make one more video where somebody on YouTube thought they found an odd perfect number. I watched the video. It was interesting and everything, but then I'll show you, true mastery of a subject and why that can't be an odd perfect number using both from my criteria and from Euler and Descartes. And then, that's what that video will be about. So, all right, under 20 minutes, not too bad. Hopefully you guys made it this far. So, signing off, as always, rule number one, do not touch other people without their consent, aka do not hurt each other. And rule number two, it's all about honesty. Lies are a tick down, aka try not to lie. All right, I'll talk to you guys later.